In the middle of the North Atlantic, one patch of ocean refuses to warm up. While the world around it heats faster every year, this single spot stays cold, almost frozen in time. Scientists call it the cold blob, and it might be the clearest sign yet that one of Earth's most important ocean systems is breaking down. We're talking about a giant current that carries heat from the tropics all the way to Europe, a hidden engine that has kept our climate stable for thousands of years. But new research in 2026 shows it has been slowing for 2 decades straight, and some scientists think it could hit a point of no return. A collapse could mean brutal winters in London, rising seas in New York, and droughts stretching across entire continents. If you enjoy stories where real science gets stranger than fiction, stick around and hit subscribe. It helps this channel grow. We are heading into the heart of the Atlantic Ocean, into a system on the edge of a historic shift. Prepare yourselves. We begin. Beneath the surface of the Atlantic Ocean, a river runs through the sea. It has no banks and no bed, only walls made of water pressure and temperature. This river carries more water than every river on land combined. Scientists call it the Atlantic Meridional Overturning Circulation, but most people just call it the conveyor belt. Picture a giant loop stretching from the tip of South America to the edge of the Arctic. Warm water starts near the equator, thick with salt and heat, and it begins a slow journey north. It hugs the east coast of the United States. It crosses toward Europe. Along the way, it releases warmth into the air above it, the same warmth that keeps entire countries livable. By the time this water reaches the cold seas near Greenland, it has given up most of its heat. It has also grown heavier, dense with salt and chilled by Arctic air. And here is where something remarkable happens. The water sinks. Thousands of feet down, it drops into the deep ocean like a stone falling through fog. Then it turns south again, crawling along the ocean floor, completing a loop that can take 1,000 years to finish. This single system moves an almost unthinkable amount of energy. Every second, it transports roughly as much heat as 90 times the energy used by all of humanity combined. Without it, average temperatures across northern Europe would likely drop several degrees within a matter of years. Winters that are merely cold could turn brutal. For centuries, humans had no idea this system even existed. Sailors felt its pull as ocean currents that helped or hindered their ships. Fishermen noticed strange temperature patterns beneath their boats, but nobody understood there was a single, connected engine driving all of it, a loop of water linking tropical heat to Arctic cold. Scientists only started taking it seriously in the last 100 years, and they only started measuring it directly in 2004, when a chain of instruments called the Rapid Array was dropped into the ocean between Florida and Africa. For the first time, researchers could watch this invisible river in something close to real time. What they found was not reassuring. Instead of a steady, predictable flow, the current showed signs of slowing. Small dips at first, the kind you might expect from natural variation, then bigger dips, then a pattern that looked less like noise and more like a trend. Today, in 2026, that trend has a name, and it comes with real numbers attached. Some studies suggest the system has already weakened by around 15% since the middle of the 20th century. That may sound small, it is not. A slowdown of this size in a system this large is like a school bus losing partial control of its brakes on a long highway. It still moves, it still functions. But something fundamental has shifted, and the further it drifts, the harder it becomes to predict what happens next. Deep beneath the waves, the conveyor belt keeps turning. But for the first time in recorded history, scientists are watching it falter in real time, and they are racing to understand what that means before the answer arrives on its own. Long before satellites and ocean sensors, one current shaped the fate of an entire continent. Sailors in the age of exploration called it the Gulf Stream, a river of warm water so powerful it could carry ships faster than the wind alone. What they did not know was that this current was doing something far bigger than pushing sails. It was keeping an entire landmass livable. The Gulf Stream forms the surface half of the larger Atlantic circulation system. It starts in the warm waters near Florida and the Gulf of Mexico, then races northeast across the ocean toward Europe. As it travels, it releases staggering amounts of heat into the atmosphere above it. That heat gets carried by wind patterns deep into countries like the United Kingdom, France, and Norway. Here is the surprising part. London sits at roughly the same latitude as parts of Canada that experience brutal snow-buried winters. Without the Gulf Stream's warmth, London would likely feel more like those frozen regions of North America. Instead, thanks to this current, the city enjoys winters that rarely dip far below freezing. The same is true across much of Northern Europe, a region that should, by latitude alone, feel far colder than it does. This is not a small climate quirk. It is the reason European agriculture developed the way it did. It is part of why cities were built where they were built, why populations grew in certain regions and not others. The warmth carried by ocean water, invisible and largely unknown to the people benefiting from it, shaped the development of an entire civilization. But the Gulf Stream does not act alone. It works in partnership with the deeper, colder return flow of the circulation system, the part that sinks near Greenland and travels back south along the ocean floor. Together they form a loop, and that loop depends on balance. Warm water must keep flowing north. Cold, salty water must keep sinking and returning south. If either half slows down, the entire system begins to wobble. Scientists have started to notice signs of exactly that kind of wobble. Surface temperature patterns near the Gulf Stream have shifted in ways that do not match normal yearly variation. Some ocean regions that should be warming alongside the rest of the planet have instead stayed unusually cool, almost as if the current delivering heat northward has started to lose its grip. A weaker Gulf Stream would not simply mean slightly cooler beaches in Florida. It could mean a fundamental change in how heat moves around the entire northern hemisphere, disrupting rainfall, storm patterns, and temperature zones far beyond the ocean itself. For hundreds of years, humans built entire nations around a current they barely understood, trusting an invisible flow of warm water to keep their world stable. Now, for the first time, that trust is being tested. The very current that helped build modern Europe may be the first clear signal that something much larger is beginning to change beneath the waves. In 2004, a team of scientists attempted something that had never been done before. They wanted to measure a river with no visible edges, a flow of water stretching across an entire ocean basin, moving in 3 dimensions at different speeds and depths. To do this, they built a chain of instruments and dropped them into the sea between the coast of Florida and the coast of Africa. This chain became known as the Rapid Array. Picture a long row of sensors anchored to the ocean floor, each one reaching up through miles of water like buoys tied to invisible strings. These instruments measured temperature, salinity, and pressure at different depths, all day, every day, feeding data back to researchers on land. Before this project, scientists could only guess at how the Atlantic circulation behaved. They relied on scattered ship measurements, taken during isolated voyages that happened to cross the right patch of ocean at the right time. It was like trying to understand a person's heartbeat by checking their pulse once a year. The Rapid Array changed that completely. For the first time, researchers had something close to a continuous heartbeat monitor for one of the planet's most important climate systems. What they discovered surprised even seasoned oceanographers. The current did not flow at a constant, steady pace. It surged and slowed throughout the year, influenced by wind patterns, seasonal temperature shifts, and other forces scientists were only beginning to untangle. Some of this variation was expected. Oceans are not static machines. But buried within the noise, a longer pattern began to emerge. Over the following 2 decades, additional monitoring arrays joined the effort, placed at different latitudes along the western edge of the Atlantic. Scientists wanted to know if the changes seen near Florida matched what was happening farther north, closer to the Arctic waters where the current eventually sinks. If the slowdown was isolated to one region, it might mean very little. If it appeared consistently across multiple locations, it would mean something much larger was underway. By 2026, researchers at the University of Miami had assembled roughly 20 years of data from 4 separate monitoring arrays. The results lined up in a way that left little room for doubt. Every single location showed the same declining trend. The current was not just fluctuating, it was weakening consistently across a massive stretch of ocean. One of the lead scientists behind the study compared the western boundary current to a warning light on a car's dashboard, the first indicator that something inside a much larger system needs attention. It does not reveal the full picture on its own, but it validates years of climate models that had predicted exactly this kind of decline. For the first time in human history, scientists were no longer relying on guesswork or ancient climate records to understand the fate of this critical system. They had 2 decades of hard, continuous data, and that data was telling them the invisible river of the Atlantic Ocean had entered a new, uncertain and closely watched phase. South of Greenland, in the middle of the North Atlantic, there is a patch of ocean behaving like nowhere else on the planet. While global temperatures climb year after year, this single region has stayed stubbornly, unusually cold. Scientists call it the cold blob, and its presence has puzzled researchers for more than a decade. At first glance, a cool patch of ocean during a warming planet might sound like good news. It is not. When scientists began investigating the cold blob more closely, they found something troubling. This is not a region cooling because of local weather. It is a region losing the warm water that should be flowing into it. Remember the conveyor belt from earlier, the loop of warm water travelling north and cold water sinking and returning south. The cold blob sits directly in the path of that northward warm flow. If the current weakens, less heat arrives in this region, and the surface water stays cooler than it otherwise would. In other words, the cold blob may be a direct fingerprint of a slowing circulation system. For years, scientists debated other possible explanations. Maybe changing wind patterns were pulling heat away from the surface. Maybe shifting cloud cover was blocking sunlight and cooling the water from above. These were reasonable questions, and researchers spent years testing them against real data. New research published in 2026 helped settle much of that debate. By comparing decades of temperature and salinity records, scientists found that wind and cloud changes alone could not explain the size or persistence of the cold blob. The pattern matched almost perfectly with a weakening Atlantic circulation, not with short-term atmospheric noise. This finding carries weight far beyond one strange patch of ocean. The cold blob sits near Europe, and its presence has already been linked to unusual weather patterns across the continent. Some researchers believe it plays a role in shifting the position of the jet stream, the fast-moving river of air high above the Atlantic that steers storms and heat waves across Europe and North America. A disturbed jet stream can trap unusually hot air in one place for weeks, contributing to dangerous heat domes even as a nearby patch of ocean stays icy cold. One climate scientist who has studied the AMOC for decades summed up the significance simply. A cold patch in a warming world is not a pause button on climate change. It is not a sign that the planet is somehow protecting itself. Instead, it may be one of the clearest visible symptoms of a much larger system starting to break down. The cold blob has become something like a bruise on the surface of the ocean, a visible mark left behind by an injury happening deep beneath the waves. And as researchers continue tracking its size and temperature, they are watching for a very specific question. Is this bruise stable, or is it still growing? For most of human history, cold weather meant one simple thing. It was cold. But climate science has revealed something almost paradoxical. Sometimes, a colder patch of ocean is actually one of the clearest signs that the planet's overall warming is accelerating a much larger, more dangerous shift. This idea confuses a lot of people at first. If the world is heating up, shouldn't every part of the ocean be getting warmer too? The answer lies in how heat actually moves around our planet. Earth's climate is not a single evenly heated system. It is a network of currents, winds and cycles constantly redistributing energy from warm regions to cold ones. When one part of that network breaks down, some areas can grow colder, even while the planet as a whole grows hotter. The cold blob near Greenland is the clearest modern example. As explained earlier, this patch stays cold because it is receiving less warm water from the Atlantic circulation system. But there is a deeper irony at work here, one that connects directly back to global warming itself. Melting ice is one of the primary reasons the circulation system is slowing down in the first place. As Greenland's massive ice sheet melts at an accelerating pace, it dumps enormous volumes of fresh water into the North Atlantic. This fresh water is lighter than the salty ocean water surrounding it, and it does not sink easily. Since the sinking of dense salty water is what powers the southern moving half of the circulation, this influx of fresh water essentially throws sand into the gears of the entire system. In simple terms, global warming is melting ice. Melting ice is diluting the ocean's salt balance, and that imbalance is slowing down the very current responsible for keeping the North Atlantic warm. The result is a strange feedback loop where the warming planet directly causes a colder pocket of ocean. This connects to a broader concept climate scientists call regional cooling within global warming. Some parts of Antarctica have shown unexpected ice growth, even as the rest of the world heats up. Certain deep ocean layers have absorbed enormous amounts of heat, while surface temperatures in specific regions lag behind. None of these patterns contradict global warming. They are symptoms of it, evidence of a planet whose systems are being pushed out of their long-standing balance. Understanding this distinction matters enormously for how people interpret climate news. A single cold snap, a chilly summer, or an unusually cool patch of ocean does not disprove a warming planet. In many cases, it can be the opposite, direct evidence that warming is disrupting systems that have remained stable for thousands of years. The cold blob is not a contradiction, it is a consequence, and as researchers continue mapping its edges and tracking its temperature, they are learning to read it not as an anomaly, but as a message written in cold water, describing exactly how a warming world can produce a chilling result. Understanding a system as vast as the Atlantic circulation requires more than a single measuring point. One monitoring array can reveal a lot, but it cannot answer the biggest questions scientists care about most. Is a slowdown happening in just one location, or is it happening everywhere at once? To answer that, researchers expanded their efforts far beyond the original RAPID array near Florida. By 2026, scientists were pulling data from 4 separate monitoring arrays, spaced out along the western edge of the Atlantic Ocean. One sat near the tropics, another stretched across the mid-latitudes. Others reached farther north, closer to the cold waters near Greenland where the current eventually sinks. Each array worked like a checkpoint along the highway of ocean water. Sensors anchored to the seafloor measured how much water was flowing past, how warm or cold it was, and how salty it had become. By comparing checkpoints spread across thousands of miles, scientists could finally trace the health of the current from the tropics all the way toward the Arctic. The stakes of this comparison were enormous. If only one checkpoint showed a slowdown, the cause might be local, a shift in nearby winds, a temporary current eddy, something explainable and contained. But if every single checkpoint showed the same declining trend, the explanation would have to be something far bigger, a change affecting the entire system from end to end. When researchers at the University of Miami finally compiled 2 decades of results from all 4 arrays, the pattern left little room for alternative explanations. Every single location showed a consistent weakening trend over the past 20 years. Not just the shallow surface currents, but deeper water layers too, the same layers responsible for carrying warmth far beneath the visible ocean surface. One of the study's lead scientists compared this consistency to a doctor checking a patient's pulse at 4 different points on their body and finding the same irregular rhythm each time. A single reading might be dismissed as a fluke. 4 matching readings, spread across enormous distances, become far harder to ignore. This wide geographic agreement also helped validate something climate models had predicted for years. Computer simulations had long suggested the Atlantic circulation would weaken under a warming climate, but real-world proof had remained elusive. Now, with 2 decades of direct observational data pointing the same direction, scientists finally had strong physical evidence matching what their models had warned about all along. Still, researchers remain cautious about overstating what this proves. The monitoring period, while significant, only covers a small slice of the ocean's long natural history. 20 years is a blink compared to the 1,000-year cycle some water molecules take to complete a single loop through the system. Yet even with that caution in mind, the agreement across 4 independent measuring stations marks a turning point in how confidently scientists can speak about this slowdown. What once looked like scattered, uncertain signals has become something closer to consensus. 4 separate sensors, spread across a vast stretch of ocean, are now telling researchers the same unsettling story. Science rarely moves in dramatic leaps. It moves in careful, incremental steps, each study building on the last until a clear picture finally emerges. In 2026, one study represented exactly that kind of turning point for the Atlantic circulation system. researchers at the University of Miami's Rosenstiel School published findings built on nearly 2 decades of continuous ocean monitoring. Their goal was ambitious. They wanted to determine, with as much confidence as the data would allow, whether the Atlantic circulation was truly weakening or whether earlier signals had simply been short-term noise. The team combined data from the 4 monitoring arrays described earlier, creating what amounted to the most complete real-world picture of this current ever assembled. Rather than relying purely on computer models or isolated measurements, they anchored their conclusions directly in physical observations, gathered continuously from the ocean itself. The results were unambiguous. Across every measured location, the western boundary contribution to the circulation system had declined steadily over roughly 20 years. This was not a single bad year skewing the numbers. It was not a short-term dip followed by recovery. It was a long, sustained downward trend, visible in the data no matter how researchers sliced it. One of the study's senior scientists described the significance in practical terms. A weaker circulation system does not simply mean colder water in one spot. It can reshape entire weather patterns, contributing to more extreme storms, shifting rainfall in unpredictable ways, and even fueling colder winters in specific regions, even as the broader planet continues warming. There is another consequence tied closely to this slowdown, one that reaches far beyond weather alone. As the circulation weakens, its ability to influence sea levels along the coastline begins to change as well. Ocean currents interact with gravity and water distribution in complex ways, and a weakening system can contribute to accelerated sea level rise in specific coastal regions, including major cities along the eastern United States. What makes this study particularly significant is not just its conclusion, but its method. For years, climate models had predicted a weakening circulation, but skeptics pointed out that models are not the same as direct evidence. This research helped close that gap. By combining real-world monitoring data with existing model predictions, scientists strengthened the case that this slowdown is not merely theoretical. The study's authors were careful to note that many questions remain unanswered. Exactly how fast the decline will continue, whether it will level off, accelerate, or reach some kind of critical threshold. These uncertainties still separate scientists from certainty. But one thing shifted permanently with this research. What had once been described using cautious language, phrases like possible weakening or potential decline, could now be described with far greater confidence. 20 years of consistent data across multiple monitoring stations does not prove a random blip. It documents a genuine, ongoing transformation happening in one of the ocean's most important systems. Scientific names often sound intimidating, packed with syllables that seem designed to confuse rather than explain. The full name of this ocean system, the Atlantic Meridional Overturning Circulation, is no exception. But hidden inside that complicated title is a surprisingly simple idea, one worth unpacking carefully before going any further. The key word is meridional. In everyday language, this word simply means north to south. Picture the lines of longitude on a globe, the vertical lines stretching from the North Pole down to the South Pole. Meridional movement follows that same north to south direction, rather than moving east to west around the planet. This distinction matters enormously for understanding how the Atlantic circulation actually works. Many ocean currents move primarily sideways, circling around ocean basins in wide loops driven mostly by wind and the rotation of the planet. The meridional circulation is different. Its defining feature is vertical, pole-to-pole movement, carrying warm water north near the surface and cold water south along the ocean floor. The word overturning captures the other essential piece of the puzzle. This describes the dramatic sinking process that happens near Greenland, where dense, cold, salty water plunges downward thousands of feet, essentially flipping from surface water into deep water. It is less like a river flowing in a flat line and more like a wheel turning on its side, water rising in one place and sinking in another, completing a full rotation over enormous stretches of time. Understanding these two words transforms the entire system from an abstract scientific term into something far more visual. Imagine an enormous vertical wheel, half floating on the ocean surface and half hidden thousands of feet below, slowly rotating as it carries heat from the equator toward the Arctic and cold water back toward the tropics. This vertical structure explains why the circulation behaves so differently from typical horizontal ocean currents. It also explains why disruptions to this system carry such serious consequences. A horizontal current redistributes water within roughly the same climate zone. A meridional current physically transports heat across dramatically different climate zones, linking the tropics and the Arctic into a single connected system. When scientists talk about this circulation weakening, they are describing a slowdown in this vertical pole-to-pole movement specifically. The sinking process near Greenland becomes less efficient. Less water plunges downward, less warm water gets pulled in to replace it. The entire vertical wheel begins turning more slowly, disrupting the careful balance that has defined Earth's climate for thousands of years. This single word, meridional, unlocks the true nature of the system scientists are racing to understand. It is not simply an ocean current moving water from place to place. It is a vertical engine, connecting the warmth of the tropics to the icy waters of the Arctic, and its slowing rotation carries consequences reaching far beyond the ocean itself. Two invisible forces control the fate of the entire Atlantic circulation system: salt and temperature. Neither one alone determines how the current behaves. It is the delicate relationship between them that keeps this massive engine running, and it is that same relationship now showing signs of serious strain. To understand why, it helps to think about density. Water becomes denser, meaning heavier for its size when it grows colder or saltier. Warm water near the tropics starts out relatively light. As it travels north along the surface, it gradually cools and gathers more salt through evaporation. By the time it reaches the frigid waters near Greenland, it has become significantly denser than the water surrounding it. This increased density is the entire secret behind the sinking process described earlier. Dense water sinks. It plunges downward through the ocean like a heavy stone dropped into a pool, pulling more surface water in behind it to replace what has descended. This continuous cycle of sinking and replacing is what powers the northward flow of warm water in the first place. Now imagine what happens if that delicate salt and temperature balance gets disrupted. This is exactly what scientists have observed happening near Greenland in recent decades. Massive amounts of fresh water, produced by rapidly melting glaciers and ice sheets, have been pouring into the North Atlantic. Fresh water is far less dense than salty ocean water, and it resists sinking in the same way. Picture pouring a thin layer of oil onto a pot of water. Instead of blending in and sinking to the bottom, the oil floats on top, disrupting the mixing process below it. Fresh glacial meltwater behaves in a somewhat similar way when it enters the salty North Atlantic. It sits closer to the surface, diluting the salt concentration and making it harder for the water beneath it to reach the density needed to sink properly. When less water sinks near Greenland, the entire circulation loses momentum. Less deep water gets pulled south along the ocean floor. Less warm surface water gets pulled north to replace what has descended. The whole system begins to slow, not because of a single dramatic event, but because of a gradual erosion of the balance that has kept it running for thousands of years. This is why melting ice sheets represent such a direct threat to ocean circulation, distinct from their more commonly discussed role in raising sea levels. It is not simply about how much water enters the ocean. It is about how that water disrupts the fundamental density differences driving one of the planet's most important climate systems. Salt and temperature might seem like small, invisible details buried within a massive, complicated ocean system, but together they form the delicate hinge holding the entire Atlantic circulation together, and that hinge is now under more pressure than at any point in recorded history. Greenland holds an ice sheet so massive it is difficult to fully picture. It stretches across roughly 660,000 square miles, an area larger than Alaska, holding enough frozen water to raise global sea levels by more than 20 feet if it were to melt entirely. For most of human history, this ice sheet remained largely stable, locked in place by consistently cold Arctic temperatures. That stability is now breaking down. As global temperatures climb, Greenland's ice sheet has begun losing mass at an accelerating pace. Massive glaciers that once crept slowly toward the sea are now flowing faster, dumping increasing volumes of fresh water and ice directly into the North Atlantic Ocean. Some regions of the ice sheet are losing ice several times faster than they were just a few decades ago. This melting matters for reasons far beyond rising sea levels alone. As explained before, the Atlantic circulation depends on a delicate balance of salt and temperature to drive its sinking process near Greenland. Every gallon of fresh meltwater entering this region works against that balance, diluting the salty water needed to power the system's vertical engine. Scientists have worked to quantify just how disruptive this influx has become. Ocean measurements near Greenland show declining salinity levels over the past several decades, a trend that lines up closely with accelerating ice loss. This is not a subtle, barely detectable shift. It represents a measurable change in the fundamental chemistry of one of the ocean's most important regions. Think of the entire circulation system as a carefully balanced machine, one that has operated the same way for thousands of years. Now imagine slowly pouring sand into that machine's gears, day after day, year after year. At first, the machine continues running, seemingly unaffected. But eventually, the accumulated interference begins to show, first as small inefficiencies, then as more serious slowdowns. Greenland's meltwater functions almost exactly like that sand. Each individual contribution might seem small on a global ocean scale, but the cumulative effect, sustained over decades of accelerating ice loss, has become significant enough for scientists to directly link it to the broader weakening trend documented throughout recent research. This creates a troubling feedback loop worth sitting with. Rising global temperatures cause Greenland's ice to melt faster. That meltwater disrupts the salt balance driving ocean circulation. A weaker circulation then alters weather patterns and heat distribution across the northern hemisphere in ways that could, in some scenarios, contribute to further climate instability. Researchers continue monitoring Greenland's ice loss alongside ocean salinity levels, treating both as critical indicators for the health of the broader circulation system. As one connects directly to the other, tracking the melting giant sitting atop Greenland has become just as important as tracking the ocean currents themselves. Buried within decades of ocean data, scientists recently uncovered something they had not expected to find: a specific moment when the entire character of Atlantic surface currents appeared to shift. Not a gradual fade, but something closer to a genuine turning point, a hinge in the timeline of an enormous ocean system. Using advanced analysis techniques, researchers identified a newly recognized pattern in Atlantic surface circulation, one they named the Atlantic convergence-divergence mode. This pattern tracks how surface currents move water together or push it apart across different regions of the ocean, offering a detailed picture of the circulation's day-to-day behavior. When scientists traced this pattern backward through decades of historical data, they discovered something striking. Around 2009, the pattern underwent a dramatic transition. Instead of a smooth, continuous decline, the data showed something closer to a step, a relatively sudden shift from one behavioral pattern to another. This finding closely matched independent observations from the Rapid Monitoring Array described in earlier chapters. Both datasets pointed toward the same general period, reinforcing the idea that something significant occurred within the Atlantic circulation system in the years following 2009. Why does this matter so much? Gradual decline and sudden transition represent two very different types of danger. A slow, steady weakening gives scientists, governments, and coastal communities time to observe, predict, and potentially adapt. A step-like transition suggests something closer to a system reorganizing itself abruptly, behaving less like a dial turning down slowly and more like a switch flipping between different states. Researchers describe this transition as a nonlinear adjustment, a term used when a system's response does not match a simple, predictable curve. Instead of weakening steadily as temperatures rose, the Atlantic surface currents appear to have reorganized their entire structure around 2009, shifting toward reduced vertical exchange and strengthened sideways flow. One particularly important detail from this research involves something called eigenmicrostate entropy, a technical measurement of how uniform or chaotic a system's underlying structure has become. Following the 2009 transition, this measurement increased noticeably, suggesting the Atlantic surface currents have entered a state that is less predictable, less locked into a single dominant pattern than before. In simpler terms, imagine a spinning top that has always wobbled in one smooth, predictable pattern. Then suddenly, without an obvious external push, its wobble changes character entirely, becoming harder to anticipate. That shift in behaviour, even without immediate collapse, signals something has fundamentally changed about the system's underlying stability. This 2009 transition does not necessarily mean collapse is imminent, but it does complicate the picture considerably. If the Atlantic circulation can undergo sudden reorganisations rather than only slow, predictable declines, then scientists face a much harder task in forecasting exactly what comes next, and exactly how much warning the world might receive before the next transition occurs. For decades, most predictions about the Atlantic circulation assumed a fairly straightforward pattern of decline. Picture a ramp, sloping gradually downward as global temperatures rise. Slow, steady, and largely predictable. New research from 2026 suggests reality may look less like a ramp and more like a staircase. A step-like decline describes a pattern where change does not happen continuously. Instead, a system remains relatively stable for a period of time, then drops suddenly to a new, lower level, then stabilizes again before potentially dropping further. Picture walking down actual stairs rather than rolling down a smooth hill. Long, flat stretches interrupted by sudden, distinct drops. This distinction carries enormous consequences for how scientists study and predict the future of the Atlantic circulation. A steady ramp-like decline is relatively straightforward to model using historical trends. Researchers can measure the rate of change and extend that same rate forward into future decades with reasonable confidence. A staircase pattern behaves completely differently. Between steps, the system might show little to no obvious change at all, potentially lulling observers into a false sense of stability. Then, seemingly without warning, another sudden drop occurs, shifting the system to an entirely new baseline. Researchers studying the Atlantic convergence-divergence mode found evidence supporting exactly this kind of pattern. Rather than smooth, continuous weakening since the industrial era began, the data pointed toward a specific transition occurring around 2009, followed by a new, altered state of behaviour that has persisted since. This raises an unsettling question. If one step has already occurred, could another step happen again? And if so, when? Scientists cannot yet answer that question with confidence. What they can say is that a step-like pattern fundamentally challenges the assumption that ocean circulation changes will always give humanity ample time to prepare. If future transitions happen suddenly, similar to the shift identified around 2009, coastal communities, agricultural systems, and weather forecasting models could face changes arriving faster than current planning accounts for. Think of it like a bridge slowly weakening under increasing weight. For a long time, the bridge might show few visible signs of stress, holding steady under loads that would have seemed dangerous decades earlier. Then, without an obvious final push, a support beam gives way, and the bridge's structural integrity shifts entirely in a matter of moments rather than years. This comparison is not meant to suggest the Atlantic circulation is on the verge of an immediate dramatic collapse. Researchers remain careful to note enormous uncertainty around future timing, but the discovery of a step-like historical pattern forces scientists to rethink how they model, predict, and communicate risk associated with this critical ocean system. Instead of a slow, predictable ramp giving humanity decades of gradual warning, the Atlantic circulation may behave more like a staircase, with long periods of apparent stability punctuated by sudden, difficult-to-predict drops, each one potentially arriving with far less warning than anyone previously assumed. Some systems in nature do not simply weaken gradually until they disappear. Instead, they exist in one of two distinct stable states, capable of holding steady in either configuration for extended periods before potentially flipping between them. Scientists increasingly believe the Atlantic circulation may behave exactly this way, a property known as B stability. To understand B stability, imagine a light switch rather than a dimmer dial. A dimmer dial allows for smooth, continuous adjustment, gradually increasing or decreasing brightness across countless possible settings. A light switch behaves completely differently. It exists in one of two states, fully on or fully off, with no meaningful stable position in between. Applied to ocean circulation, this concept suggests the Atlantic system might naturally settle into one of two distinct configurations. One state resembles the strong, active circulation that has defined the past several thousand years, efficiently carrying warm water north and cold water south. The other represents a weak, largely collapsed state, where this vertical exchange slows dramatically or stops altogether. Crucially, bistability implies that transitioning between these two states does not necessarily happen smoothly. A system stuck in the strong state might resist gradual change for a long period, even as underlying conditions shift. But once conditions cross a certain threshold, the system could shift relatively rapidly toward the weaker state, similar to flipping that light switch rather than slowly turning down a dial. Recent research reviewing decades of evidence found growing support for this idea. Scientists studying ancient climate records identified past periods when the Atlantic circulation appears to have existed in this weaker, collapsed configuration, particularly during past ice ages. So this historical evidence strengthens the case that bistability is not simply a theoretical possibility, but a genuine characteristic of how this system has behaved before. A 2026 review of existing research went further, concluding that current evidence suggests the present-day Atlantic circulation is indeed operating within this bistable framework right now. In other words, the system may already exist in a configuration capable of shifting toward its weaker state, rather than sitting in some entirely different single-state arrangement immune to this kind of dramatic transition. This distinction matters enormously for predicting future risk. A system that changes smoothly and continuously allows for relatively confident forecasting, since small changes in conditions produce correspondingly small changes in outcome. A bistable system behaves far less predictably. Small, seemingly minor shifts in underlying conditions could eventually push the system past a critical threshold, triggering a much larger, faster transition than the initial change would suggest. Scientists remain divided on exactly how close the Atlantic circulation currently sits to that critical threshold. Some believe substantial buffer remains before any dramatic transition becomes likely. Others argue the system may be closer to that tipping point than previously assumed. What researchers increasingly agree on, however, is the underlying architecture of the system itself. This is not simply a dial capable of infinite gradual adjustment. It is closer to a switch, holding steady in one configuration until conditions finally force it toward the other. Not every change in nature happens gradually. Some systems hold steady for long stretches of time, seemingly resistant to outside pressure, only to shift suddenly once a specific threshold gets crossed. Scientists call this a tipping point, and it represents one of the most important and most difficult to predict concepts in modern climate science. A tipping point describes the moment when a system moves from one stable state into another, often quickly and sometimes irreversibly. Unlike gradual change, which allows for careful monitoring and course correction, a tipping point can arrive with relatively little advance warning, especially if the system in question shows few obvious external signs of strain right up until the threshold is crossed. Applied to the Atlantic circulation, a tipping point would represent the moment this system shifts decisively from its current, relatively strong configuration into a dramatically weaker or fully collapsed state. Based on the bistability concept explored earlier, once this threshold is crossed, reversing course could become extremely difficult, potentially requiring conditions to change far more dramatically than what originally caused the shift in the first place. This asymmetry between crossing a threshold and reversing it represents one of the most concerning aspects of tipping point behavior. Imagine pushing a large boulder resting near the edge of a hill. For a long time, the boulder might resist your efforts, barely shifting despite continuous pressure. But once it finally tips past a certain point, it does not simply return to its original position when the pressure stops. It rolls downward, gathering momentum, potentially travelling far beyond where a simple, reversible nudge would have taken it. Climate scientists studying the Atlantic circulation have spent years attempting to develop reliable early warning indicators, physical signs that might reveal how close the system sits to crossing its own tipping point. Recent research has focused on subtle changes in ocean salinity patterns, surface current behavior, and the specific structural transitions described in earlier chapters, all in an effort to detect warning signs before an actual collapse begins. Some of this research has produced troubling conclusions. Certain physics-based early warning signals suggest the circulation may currently be on what researchers describe as a tipping course, meaning existing trends if they continue uninterrupted, could eventually lead the system across its critical threshold. However, enormous uncertainty remains embedded within these predictions. Climate models continue to disagree substantially on both the exact location of this threshold and how much time remains before it might be reached. Some researchers believe a full collapse remains centuries away, if it happens at all. Others argue conditions could align to trigger a transition within just a few decades. This uncertainty does not diminish the seriousness of the underlying concern. It highlights exactly why tipping points prove so dangerous within complex systems like ocean circulation. A system can appear relatively stable for years, even decades, right up until conditions finally align to push it past the edge, at which point the transition itself could unfold far faster than anyone anticipated. 12,000 years ago, Europe experienced one of the most dramatic climate reversals in the planet's recent history. A period of gradual warming, following the end of the last ice age, suddenly and violently reversed course. Within the span of a single human generation, temperatures across the region plunging much of the continent back into ice age conditions that lasted for more than 1,000 years. Scientists call this event the Younger Dryas, and it stands today as one of the clearest historical examples of what can happen when the Atlantic circulation system experiences a sudden, dramatic disruption. The likely trigger for this ancient event involved a massive glacial lake, formed from meltwater trapped behind a wall of retreating ice somewhere across North America. When that natural ice dam eventually failed, an enormous surge of fresh water poured suddenly into the North Atlantic Ocean, disrupting the same delicate salt and temperature balance explored earlier. This sudden influx of fresh water appears to have significantly weakened, or possibly even temporarily shut down, the Atlantic circulation system entirely. Without its usual supply of warm water travelling north from the tropics, temperatures across Europe and parts of North America plummeted rapidly. Evidence found in ancient ice cores and sediment layers shows temperatures in some regions dropping by several degrees within just a few decades, an incredibly fast shift by geological standards. The Younger Dryas offers modern scientists something invaluable: real-world proof that this circulation system is capable of dramatic, relatively sudden collapse under the right conditions. It also demonstrates just how significant the consequences of that kind of collapse can be, transforming an entire continent's climate within a timeframe far shorter than most people would expect from natural processes. Researchers studying this ancient event have drawn direct comparisons to conditions unfolding today. Just as ancient glacial meltwater disrupted ocean salinity thousands of years ago, modern Greenland ice melt is introducing similar disruptions into the same general region of ocean. The scale differs considerably between these two events, and scientists remain careful not to suggest an identical repeat is guaranteed. But the underlying mechanism, freshwater disrupting the circulation's delicate balance, remains strikingly similar. This historical precedent carries significant weight within modern climate research. It transforms discussions about a potential future circulation collapse from purely theoretical modelling into something grounded in documented physical history. The Atlantic circulation has shut down before. Ancient evidence proves it. And when it did, the resulting climate shift arrived far faster and far more severely than gradual centuries-long change would predict. Understanding the Younger Dryas provides essential context for everything explored. This is not simply a modern computer model predicting a hypothetical future scenario. It represents a documented example, written directly into Earth's geological record, of exactly the kind of transformation scientists now worry could unfold again. Long after the ancient Younger Dryas event, Europe experienced another notable cold period, one occurring much closer to modern times and offering scientists an additional case study for understanding how the Atlantic circulation influences regional climate. Beginning sometime around the 14th century and lasting for several hundred years, this era became known as the Little Ice Age. During this period, parts of Europe experienced significantly colder winters than the centuries immediately before or after it. Historical records describe rivers freezing solid enough for people to walk across them regularly. Paintings from this era frequently depict snow-covered landscapes and frozen canals, scenes that would become far less common in the following centuries as temperatures gradually recovered. The exact causes behind the Little Ice Age remain debated among historians and scientists alike. Several factors likely contributed simultaneously, including reduced solar activity and increased volcanic eruptions that temporarily blocked sunlight. However, growing evidence suggests disruptions to the Atlantic circulation may have also played a meaningful role in intensifying and extending this cold period. Unlike the dramatic, relatively sudden Younger Dryas event thousands of years earlier, the Little Ice Age appears to represent a more modest disruption, a partial weakening rather than a full-scale collapse. This distinction matters significantly for modern climate science, because it demonstrates that even smaller disturbances to the circulation system can meaningfully influence regional climate patterns without requiring a complete system shutdown. This historical example provides an important middle ground for understanding potential future risk. The Younger Dryas demonstrates what a full, dramatic collapse looks like. The Little Ice Age demonstrates that partial weakening alone, even without complete shutdown, carries the potential to noticeably alter regional weather patterns for centuries at a time. Modern researchers studying today's ongoing circulation slowdown have drawn direct comparisons to this medieval period. If a relatively modest disruption several centuries ago was capable of producing multiple generations of colder winters across Europe, then today's more significant weakening trend, backed by 2 decades of consistent observational data, raises legitimate concerns about similarly impactful regional cooling in the coming decades. There is an important distinction worth emphasizing here as well. Unlike the Little Ice Age, which occurred alongside relatively stable global temperatures, today's circulation weakening is unfolding during a period of rapid overall planetary warming. This creates a genuinely unusual scenario, one without a clean historical parallel. Regional cooling driven by a weakening circulation system, occurring simultaneously alongside significant global warming elsewhere. Scientists continue studying both historical examples carefully, searching for insights into how the modern Atlantic circulation might behave as it continues weakening. The lessons drawn from centuries past cannot perfectly predict the future, but they offer something invaluable nonetheless. Concrete historical proof that even partial disruptions to this critical system carry consequences capable of reshaping the climate experienced by generations of people living through them. For years, computer models predicting the future of the Atlantic circulation carried a consistent, troubling pattern. When researchers eventually compared those predictions against real-world observations, the models almost always underestimated just how quickly the circulation was actually weakening. This gap between prediction and reality matters enormously. Climate models represent some of the most sophisticated scientific tools ever developed, built using enormous amounts of data and tested repeatedly against historical climate patterns. When these models consistently miss the mark in the same direction, understanding exactly why becomes a critical scientific priority. Researchers investigating this pattern identified several likely explanations. Many climate models struggle to fully capture small-scale ocean processes, tiny swirling eddies, and localized mixing patterns that individually seem insignificant, but collectively influence how efficiently heat and salt get distributed across large ocean regions. A 2026 study specifically found that models incorporating these fine-scale ocean dynamics predicted a notably weaker response to Greenland's meltwater than older, simpler models had assumed. Additionally, many existing models have historically underestimated exactly how quickly Greenland's ice sheet would lose mass under continued warming. Since meltwater plays such a critical role in disrupting the circulation salt balance, an underestimated melting rate naturally produces an underestimated slowdown in the broader circulation system as well. This consistent gap between model predictions and real-world observations carries serious implications for how confidently scientists can forecast future risk. If existing models have repeatedly underestimated the pace of decline throughout recent decades, it raises an uncomfortable question about their reliability moving forward. Are current predictions about future decades similarly too conservative? Some scientists argue exactly that. Recent studies combining direct ocean observations with existing climate models concluded that most current projections likely underestimate how much the circulation will weaken by the end of this century. Rather than assuming existing predictions represent a reasonable outer limit, these researchers suggest reality could ultimately track closer to the more severe end of established forecasts, or potentially beyond them entirely. This does not mean every prediction about the Atlantic circulation is destined to be wrong. Climate science continues improving rapidly, incorporating increasingly detailed ocean physics and higher resolution modeling techniques with each passing year. The models available today are already significantly more sophisticated than those used even a decade ago. But the historical pattern of underestimation serves as an important caution for anyone interpreting current forecasts. When scientists say the Atlantic circulation could weaken by a certain percentage over the coming decades, that number likely represents a reasonably conservative estimate rather than a worst-case scenario. Given the pattern of consistent underestimation observed throughout recent research history, the true pace of change happening beneath the waves may ultimately outrun even today's most careful predictions. Numbers rarely capture the full weight of a scientific finding on their own, but one figure has become central to nearly every conversation about the future of the Atlantic circulation: 50%. According to recent research published in 2026, the circulation system could weaken by roughly half its current strength by the year 2100. To understand why this number matters so much, it helps to picture the circulation as it exists today: a massive continuous flow of water moving heat from the tropics toward the Arctic. A 50% weakening does not mean the system disappears entirely. It means the engine driving this flow operates at roughly half its historical strength, delivering significantly less heat, less moisture redistribution, and less overall climate stability than the system humanity has relied on for thousands of years. This estimate comes from combining decades of direct ocean observations with increasingly sophisticated climate models, the same combination of tools explored before. Researchers cross-referenced real-world measurements against model projections, adjusting for the historical pattern of underestimation identified in earlier studies. A 50% reduction represents a scenario significant enough to reshape weather patterns across multiple continents. Consider it like a home heating system suddenly losing half its capacity during the coldest months of winter. The house does not become uninhabitable overnight, but comfort, stability, and safety margins all shrink dramatically, especially during periods of extreme weather. Applied to the Atlantic circulation, a 50% weakening could mean less reliable warmth reaching northern Europe, disrupted rainfall patterns stretching from South America to Africa, and increasingly unpredictable storm behavior along the eastern coastline of the United States. None of these consequences would necessarily happen instantly or uniformly. Instead, they would likely unfold gradually, then increasingly manifest as extreme weather events grow more frequent and more severe. It is important to understand what this 50% estimate does not represent. It is not a prediction of complete collapse, the full shutdown scenario explored through historical examples like the Younger Dryas. Instead, it describes a significantly weakened, but still partially functioning system, one operating well outside the boundaries of anything experienced during recorded human history. Scientists emphasize that this figure carries considerable uncertainty. Some models suggest weakening could remain below this threshold if global emissions decline significantly in the coming decades. Others warn the decline could exceed 50%, particularly if Greenland's ice loss continues accelerating at its current pace, or if additional tipping points get triggered along the way. What makes this 50% figure so significant is not its precision, but its magnitude. It represents a fundamental transformation of one of the Earth's most important climate systems, unfolding within a time frame measured in decades rather than centuries. For a system that has remained relatively stable across thousands of years of human civilization, a shift of this scale marks unprecedented territory, and scientists are only beginning to understand exactly what that territory might look like. While most projections about the Atlantic circulation focus on gradual weakening throughout this century, a smaller group of researchers has proposed something far more urgent. According to their calculations, full collapse of the circulation system could theoretically occur far sooner than most people assume, potentially beginning anywhere between 2025 and 2095. This research, led by scientists studying centuries of historical climate data, uses statistical techniques designed to detect early warning signs of an approaching tipping point. Rather than relying purely on physical ocean models, this approach analyzes patterns of instability within existing data, searching for the kind of subtle wobbling that often precedes a system's sudden shift from one stable state into another. The scientists behind this research describe their findings using unusually direct language for the field of climate science. One lead researcher stated plainly that this would represent an enormous change, emphasizing that the circulation is not fully shut down. for approximately 12,000 years since the ancient Younger Dryas event, it is critical to understand that this particular prediction remains highly controversial within the broader scientific community. Many oceanographers argue that current evidence does not support such an early timeline, suggesting instead that any potential collapse likely remains many decades, if not centuries, away. Other researchers believe today's warming pace simply is not intense enough yet to trigger a near-term shutdown. This disagreement does not necessarily mean one side is right and the other wrong. It reflects the genuine significant uncertainty still surrounding this incredibly complex system. Ocean circulation involves countless interacting variables, from ice melt rates to wind patterns to deep ocean mixing processes that remain difficult to measure with complete precision, even using today's most advanced monitoring technology. What makes this particular research significant, regardless of whether its specific timeline proves accurate, is the wide range of uncertainty it highlights. A collapse window stretching from 2025 to 2095 spans an enormous 70-year period, illustrating just how much scientists still do not know about exactly when, or even whether, a full transition will occur. This uncertainty creates a genuinely difficult challenge for policymakers, coastal communities, and anyone attempting to plan for potential future climate scenarios. Should preparations proceed as though collapse could arrive within the next decade, or should planning assume a much longer, more distant timeline? Most climate scientists studying this issue advocate for a cautious, evidence-based middle ground, treating early collapse scenarios as a legitimate possibility worth preparing for, without assuming it as a certainty. Given the severity of potential consequences, many researchers argue that even a relatively small probability of near-term collapse justifies taking the risk seriously, rather than dismissing it simply because significant uncertainty remains. The clock, according to this smaller group of researchers, may already be running. Whether it reads decades or mere years remains one of the most contested, high-stakes questions in modern climate science. Anyone following news coverage of the Atlantic circulation quickly notices something confusing. Some scientists describe an urgent crisis potentially unfolding within years. Others describe a slow, multi-century process posing little, immediate risk. Understanding why researchers studying the exact same ocean system reach such different conclusions reveals a lot about how complex climate science actually works. Part of this disagreement stems from differing research approaches. Some scientists rely primarily on physical ocean models, complex computer simulations built using known laws of fluid dynamics, heat transfer, and salt distribution. These models tend to produce more conservative, gradual predictions, largely because they are built directly upon well-established physical principles that resist dramatic, sudden shifts. Other researchers rely more heavily on statistical analysis of historical data, searching for patterns of instability that might indicate an approaching tipping point. This approach can potentially detect early warning signs that physical models might miss entirely, but it also carries greater uncertainty, since it depends heavily on interpreting subtle statistical patterns rather than directly simulating known physical processes. Neither approach is inherently more correct than the other. Each offers valuable insight while carrying its own particular limitations. Physical models excel at simulating known processes, but may struggle to anticipate unprecedented behavior. Statistical approaches can potentially flag early warning signs, but may also produce false alarms, mistaking normal variation for genuine instability. Another significant source of disagreement involves interpreting historical data. The Atlantic circulation has only been continuously monitored using modern instruments since 2004, providing scientists with roughly 2 decades of high-quality direct measurements. Compared to a system that operates across timescales spanning centuries or even millennia, 20 years represents an incredibly small sample size, similar to trying to understand someone's entire life story based on a single afternoon. This limited monitoring window forces scientists to rely heavily on historical proxy data, indirect evidence extracted from sources like ice cores, ocean sediment layers, and ancient temperature records. Interpreting this kind of proxy evidence often requires significant scientific judgment, and different research teams sometimes reach different conclusions when analysing similar underlying data sets. Despite these disagreements, it would be inaccurate to suggest scientists disagree about everything related to the Atlantic circulation. Nearly universal consensus exists around several key points. The circulation is genuinely weakening. Human-caused climate change, primarily through accelerated Greenland ice melt, represents the primary driver behind this weakening. And continued warming increases the overall risk of more severe disruption occurring at some point during the coming decades or centuries. The genuine disagreement centers specifically on timing and probability, not on whether meaningful change is happening at all. Some scientists believe humanity has considerable time to respond and adapt. Others worry the window for meaningful action may be closing far faster than most people realize. This scientific uncertainty does not represent a weakness in climate research. It reflects the genuine complexity of studying one of the most intricate systems on the entire planet, using tools and monitoring technology that have only existed for a relatively short period of scientific history. Imagine stepping outside in London during what should be a typical winter morning, only to find temperatures plunging to levels rarely experienced anywhere in modern British history. According to recent climate modelling, this scenario could become a regular occurrence if the Atlantic circulation eventually collapses or weakens dramatically. Research published in 2025 examined exactly what a significant circulation collapse would mean for European winters, even under a moderate global warming scenario of roughly 2 degrees Celsius above pre-industrial temperatures. The findings painted a dramatically different picture than most people associate with a warming planet. According to this research, extreme winter cold events in northwestern Europe could intensify significantly following a circulation collapse. Record low temperatures in London could potentially plunge to levels around -4 degrees Fahrenheit, a level of cold rarely, if ever, experienced in the city's recorded history. Scandinavian countries could face even more extreme conditions, with record cold potentially reaching -58 degrees Fahrenheit in some regions. Beyond these extreme record-breaking events, researchers also examined how frequently milder but still severe frost days might occur. In the Netherlands, for example, current climate patterns produce an average of roughly 53 frost days annually. Following a circulation collapse, that number could climb dramatically, potentially reaching between 150 and 180 frost days each year, transforming winter from an occasional inconvenience into a defining months-long feature of daily life. This dramatic cooling would occur specifically because northwestern Europe currently receives an enormous, largely invisible subsidy of warmth from the Atlantic circulation system. Remove or significantly weaken that subsidy, and regional temperatures would likely fall toward levels more consistent with their actual latitude, similar to conditions experienced in far colder regions of North America, located at similar distances from the equator. Beyond temperature alone, researchers also project significant changes to precipitation patterns across the continent. Rainfall distribution would likely shift substantially, potentially drying out certain regions while making others considerably wetter, disrupting agricultural systems that have operated under relatively stable climate conditions for generations. It is important to understand the apparent contradiction embedded within this scenario. A collapsing Atlantic circulation exists directly because of global warming, driven primarily by accelerated Greenland ice melt. Yet the direct regional consequence for Europe could involve significantly colder temperatures, not warmer ones, creating one of climate science's most counterintuitive and difficult to communicate outcomes. This regional cooling effect does not contradict the broader reality of global warming happening across the rest of the planet. It represents a striking example of how a warming world can simultaneously produce dramatically colder conditions within specific regions, disrupting long-held assumptions about what climate change actually looks like on the ground, particularly for the millions of people living across northwestern Europe. For centuries, countries across northwestern Europe built their infrastructure, agriculture, and daily life around a climate that remained relatively mild compared to their actual geographic latitude. A significant Atlantic circulation collapse would force these nations to confront an entirely different reality, one requiring adaptation on a scale rarely seen throughout modern history. Consider the practical implications of the extreme cold projections explored earlier. Countries like the United Kingdom currently operate with relatively limited infrastructure built for severe winter conditions, especially compared to nations like Canada or Russia that experience harsh cold as a routine, expected part of annual life. Heating systems, building insulation standards, transportation networks, and emergency response systems have all developed around a historically mild climate baseline. A dramatic cooling event would require rapid infrastructure adaptation across multiple sectors simultaneously. Home heating systems designed for occasional cold snaps would need significant upgrades to handle months of sustained, severe cold. Transportation networks unfamiliar with heavy, persistent snow and ice could face serious disruptions, similar to the kind of widespread paralysis seen when unusually severe winter storms occasionally strike regions unprepared for extreme cold. Agriculture represents another area facing substantial disruption. Many crops currently grown across northwestern Europe depend on relatively mild winter conditions and predictable growing seasons. A dramatic shift toward harsher, longer winters could force widespread changes in farming practices, potentially requiring shifts toward different crop varieties better suited to colder climates, similar to those currently grown across more northern regions of the world. Energy demand would likely surge dramatically under these conditions as well. Heating an entire region through months of severe cold requires enormous amounts of energy, potentially straining existing power grids that were not originally designed to handle this level of sustained winter demand. Countries would face difficult decisions about energy infrastructure investment, balancing the need for reliable heating against existing climate commitments focused on reducing fossil fuel consumption. Beyond physical infrastructure, this kind of dramatic climate shift would also carry significant economic and social consequences. Industries built around historically mild winters, from construction to outdoor tourism, would need to adapt substantially. Public health systems would need to prepare for increased cold-related illness and injury, particularly among vulnerable populations less accustomed to severe winter conditions. Some researchers point to countries like Canada and parts of Scandinavia as potential models for adaptation, noting these regions have already developed extensive infrastructure and cultural practices specifically suited to harsh winter conditions. However, adapting existing densely populated European cities to a completely different climate reality within just a few decades would represent an enormous, costly, and logistically complex undertaking, unlike anything most of these nations have previously faced. This chapter of the Atlantic circulation story extends far beyond abstract climate science into the practical, immediate challenges facing millions of people. A collapsing ocean current thousands of miles offshore could ultimately reshape how entire nations build homes, grow food, and plan for the future, forcing rapid adaptation to a climate reality few currently anticipate experiencing within their own lifetimes. While Europe potentially faces dramatic cooling, the eastern coastline of the United States confronts a very different threat tied to the same weakening Atlantic circulation system. Rising sea levels, already a growing concern across coastal American cities, could accelerate significantly as this critical ocean current continues losing strength. This connection between ocean circulation and sea level might initially seem surprising. Most discussions about rising seas focus primarily on melting ice sheets and thermal expansion, water physically expanding as it warms. However, ocean circulation patterns also play a direct, measurable role in determining exactly how sea levels distribute across different coastal regions. The Atlantic circulation actually helps hold sea levels along the eastern United States slightly lower than they would otherwise sit, through a complex interaction between ocean currents and coastal water buildup. As this circulation weakens, that effect diminishes, allowing sea levels along the American coastline to rise faster than the global average increase caused by melting ice and warming oceans alone. Recent research examining historical circulation slowdowns found direct evidence supporting this connection. During previous periods of significant Atlantic circulation weakening, sea levels along the northeastern United States rose measurably faster than during periods when the circulation remained relatively stable, confirming a direct physical relationship between these two seemingly separate phenomena. This accelerated sea level rise would compound existing flood risks already facing major coastal cities. New York, Boston, and Miami all sit in vulnerable, low-lying coastal areas where even modest increases in sea level can dramatically expand flood risk during storms and unusually high tides. To put this risk into perspective, consider a familiar landmark. The Fearless Girl statue standing near the New York Stock Exchange measures roughly 4 feet tall. under certain collapse scenarios modeled by researchers, potential flooding in New York's financial district could reach water levels rising to the statue's shoulders, illustrating just how significant this kind of flooding could become within one of the country's most economically important districts. Beyond direct flooding from rising baseline sea levels, this shift would also amplify the destructive power of hurricanes and coastal storms. Hurricane Sandy, which struck the New York area in 2012, caused approximately $8 billion in additional economic damage directly attributable to just a few inches of climate-driven sea level rise beyond historical baselines. A significantly weakened Atlantic circulation could push baseline sea levels considerably higher than during Sandy, dramatically increasing the potential damage from future storms of similar or lesser intensity. This represents one of the clearest, most immediate ways a weakening ocean, current thousands of miles away, could directly impact daily life for millions of Americans living along the eastern seaboard, transforming an abstract scientific finding into concrete, measurable risk facing some of the nation's largest and most economically vital coastal cities. Understanding exactly why a weakening ocean current affects sea levels requires exploring a surprising connection between ocean water and gravity itself, a relationship most people never consider when thinking about rising seas. Massive amounts of moving water actually exert a measurable gravitational pull, subtly influencing how ocean water distributes across the planet's surface. The Atlantic circulation, given its enormous scale, generates enough gravitational influence to measurably affect sea levels along certain coastlines, particularly along the eastern United States. This gravitational relationship helps explain a pattern researchers have observed for years. As the Atlantic circulation has weakened, its gravitational pull on surrounding ocean water has correspondingly diminished as well. Reduced gravitational pull allows water that would otherwise be drawn toward the current's path to instead redistribute elsewhere, including toward coastal regions along the eastern United States. Picture a large magnet sitting near a pile of metal filings, subtly pulling them into a particular pattern. As that magnet weakens, the filings gradually redistribute, spreading more evenly rather than concentrating tightly around the magnet's original position. Ocean water behaves in a somewhat similar way, in response to the Atlantic circulation's gravitational influence, redistributing as that influence changes over time. This effect compounds directly with the other sea level factors explored earlier, including melting ice sheets and warming ocean water expanding in volume. Rather than representing a separate, isolated phenomenon, changing gravitational influence works alongside these other factors, contributing to the specific pattern of accelerated sea level rise observed along the eastern American coastline. Scientists have used this gravitational relationship to help explain a particularly puzzling pattern in coastal sea level data. Different coastal regions around the world experience meaningfully different rates of sea level rise, even when accounting for local factors like land subsidence or regional ocean warming. The Atlantic circulation's gravitational influence helps explain part of this puzzling geographic variation, particularly for regions closest to the current's historical path. This gravitational connection reveals just how deeply interconnected different aspects of Earth's climate system truly are. A weakening ocean current does not simply mean less heat transported northward. It means subtle shifts in gravitational forces rippling outward to influence exactly how ocean water distributes across thousands of miles of coastline, ultimately determining which communities face the greatest flood risk in the coming decades. Understanding this connection helps explain why scientists studying the Atlantic circulation pay such close attention to seemingly small changes in current strength. Even modest weakening carries consequences extending far beyond the ocean itself, reaching directly into the daily lives of coastal communities through a surprising, largely invisible gravitational relationship most people never knew existed. Among all the coastal regions potentially facing increased flood risk from a weakening Atlantic circulation, two American metropolitan areas stand out prominently in recent research: New York City and South Florida. Together, these regions illustrate just how significant the economic stakes have become. Recent analysis combining climate modeling with detailed economic data examined exactly what a significant circulation collapse could mean for coastal flooding across major American cities. The findings suggest flood risk in both the Miami and New York City metropolitan areas could effectively double compared to current levels, transforming already vulnerable coastal regions into areas facing dramatically increased exposure to costly flooding events. South Florida faces particularly severe projected impacts. Researchers estimate this region alone could account for roughly half of all projected flood exposure increases across the entire eastern coastline following a significant circulation collapse, with potential losses reaching approximately $500 million. This concentration of risk stems partly from South Florida's uniquely vulnerable geography, with over 2 million residents currently living within just 4 feet of the local high tide line. New York City faces its own substantial projected increases in flood exposure. Under collapse scenarios examined by researchers, flood exposure across the New York metropolitan area could more than double relative to current levels, with potential losses reaching approximately $270 million across the city and surrounding communities. Perhaps most concerning, this research suggests the impact would not remain confined to areas already considered high risk today. Researchers identified more than 100 zip codes spread across 12 different states that currently face little to no meaningful coastal flood risk, but would likely develop significant flood exposure following a substantial circulation collapse scenario. This expansion into previously low-risk areas represents a particularly challenging consequence for emergency planning and infrastructure investment. Communities that have never needed to consider serious flood mitigation measures could suddenly find themselves facing risks similar to those currently experienced by long-established coastal flood zones, without decades of accumulated experience or existing infrastructure designed to handle this kind of exposure. The economic implications extend beyond direct flood damage costs alone. Insurance markets, property values, and long-term infrastructure investment decisions across these regions would likely need significant adjustment to account for dramatically increased flood risk. Some coastal areas could face substantial economic disruption even before any actual flooding occurs, simply through markets adjusting to reflect this newly elevated risk profile. These projections illustrate something important about the broader Atlantic circulation story. While much of the conversation focuses on abstract scientific concepts like ocean salinity and circulation strength, the ultimate consequences translate directly into concrete economic and human costs, concentrated specifically within some of America's largest, most densely populated coastal metropolitan areas. Hurricane season along the eastern United States has always carried inherent unpredictability, but a significantly weakened Atlantic circulation could introduce an entirely new layer of uncertainty into already complex storm forecasting, potentially producing more erratic and more intense coastal storms than historical patterns would suggest. The relationship between ocean circulation and hurricane behavior involves several interconnected factors. Ocean surface temperature plays a critical role in fueling hurricane intensity, with warmer water generally providing more energy for storms to strengthen as they travel across open ocean. A weakening Atlantic circulation disrupts normal temperature distribution patterns across the ocean, potentially creating unusual pockets of unusually warm or unusually cool water in regions that typically maintain more predictable temperature patterns. These disrupted temperature patterns could influence hurricane behavior in genuinely unpredictable ways. Storms might intensify more rapidly than historical models would suggest when passing over unexpectedly warm ocean regions. Alternatively, storms could weaken unexpectedly when encountering colder patches of water, similar to the persistent cold blob explored earlier, disrupting the reliability of existing forecasting models built around historical temperature patterns. Beyond direct ocean temperature effects, a weakening circulation could also influence broader atmospheric patterns that steer hurricanes toward or away from populated coastal areas. Changes to the jet stream, partially connected to circulation weakening through disruptions near the cold blob region, could alter the typical paths storms follow as they move across the Atlantic Ocean, potentially sending storms toward regions less accustomed to significant hurricane impacts. Combined with the accelerated sea level rise, even hurricanes of similar intensity to historical storms could produce significantly more destructive flooding along affected coastlines. Higher baseline sea levels mean storm surge, the wall of ocean water pushed ashore during a hurricane, would reach further inland and cause more extensive damage than an identical storm would have produced just a few decades earlier. Climate researchers examining historical data have already identified troubling patterns potentially connected to circulation weakening. Some studies suggest hurricanes, forming under conditions resembling a weaker Atlantic circulation, tend to intensify more rapidly and reach higher peak intensities compared to storms forming under more historically typical ocean conditions. This combination of factors, disrupted temperature patterns, altered storm paths, and elevated baseline sea levels, creates a genuinely challenging forecasting environment for meteorologists and emergency planners alike. Historical hurricane data, collected over decades of relatively stable circulation conditions, may become progressively less reliable for predicting storm behaviour as the underlying ocean system continues shifting into unfamiliar territory. For coastal communities across the eastern United States, this uncertainty translates directly into increased real-world risk. Storms may become harder to predict with existing tools, potentially arriving with less warning or producing more severe impacts than historical experience would suggest, forcing emergency planners to confront an increasingly unpredictable hurricane landscape shaped by forces unfolding deep beneath the ocean's surface. While coastal regions along the eastern United States brace for rising seas and intensifying storms, an entirely different threat looms over the country's central and western regions, a potential decline in rainfall and snowfall that could reshape agriculture and water availability across a massive stretch of American territory. This connection between a distant ocean current and inland precipitation might initially seem difficult to understand, but it stems directly from the Atlantic circulation's broader role in shaping large-scale atmospheric patterns across North America. Ocean currents influence far more than local coastal weather. They help drive massive atmospheric circulation patterns that determine where moisture travels and where it eventually falls as rain or snow. Research examining potential circulation collapse scenarios has identified troubling projections specifically for America's interior regions. According to these studies, a significant weakening or collapse of the Atlantic circulation could lead to substantially reduced precipitation across large portions of the central and western United States, disrupting rainfall and snowfall patterns that regional agriculture and water systems have depended upon for generations. This kind of disruption carries enormous practical consequences. Much of America's agricultural production relies on relatively predictable, seasonal precipitation patterns, timed carefully around planting and harvest cycles developed over decades of relatively stable historical climate conditions. Significant disruptions to this rainfall timing could force major adjustments to farming practices across some of the most agriculturally productive regions in the entire country. Snowfall reduction carries its own distinct consequences, particularly across western mountain regions. Many western states depend heavily on winter snowpack as a natural water storage system, with melting snow throughout spring and summer providing a critical, steady water supply for both agriculture and growing urban populations. Reduced snowfall could significantly diminish this natural water storage capacity, potentially intensifying water scarcity issues that many western states already struggle with today. Scientists studying these precipitation shifts emphasize that the exact regional patterns remain difficult to predict with complete precision. Climate systems involve countless interacting variables, and researchers continue refining models to better understand exactly which specific regions might experience the most significant reductions in rainfall and snowfall following substantial circulation changes. However, the broader pattern identified across multiple independent studies remains consistent. A weakened Atlantic circulation appears likely to disrupt established precipitation patterns across a significant portion of the American interior, moving beyond the more commonly discussed coastal impacts. This represents an important reminder about the far-reaching influence of ocean circulation systems. The consequences of a weakening Atlantic current do not remain confined to coastal regions alone. They extend deep into the continental interior, potentially reshaping water availability and agricultural viability across states located thousands of miles from the nearest ocean coastline, illustrating just how interconnected Earth's climate systems truly are. Thousands of miles from the cold waters near Greenland, an entirely different region faces potentially devastating consequences tied to the same weakening ocean circulation system. Across large portions of Africa, seasonal monsoon rains represent an absolutely critical lifeline, supporting agriculture, drinking water supplies, and daily survival for hundreds of millions of people. The connection between Atlantic circulation and African rainfall involves complex atmospheric relationships developed over thousands of years of relatively stable climate patterns. Ocean temperature differences across the Atlantic help drive the position and strength of seasonal monsoon systems, the concentrated periods of heavy rainfall that many African regions depend upon for the vast majority of their annual water supply. Research examining potential circulation collapse scenarios consistently identifies significant drought risk across parts of Africa as one of the most severe potential consequences. Even relatively modest historical disruptions to the Atlantic circulation, similar to the medieval period, have been linked to serious drought conditions across African regions, illustrating just how sensitive this rainfall system can be to changes happening thousands of miles away. A full collapse scenario would likely intensify these effects dramatically. Reduced or shifted monsoon rainfall could translate directly into extended severe drought conditions across some of the most vulnerable agricultural regions on the entire planet. Regions where many communities already face significant challenges maintaining reliable access to food and water, even under current relatively stable climate conditions. The human stakes involved in this potential scenario are difficult to overstate. Hundreds of millions of people across Africa depend directly on rain-fed agriculture, farming systems entirely reliant on predictable seasonal rainfall rather than extensive irrigation infrastructure. Significant disruptions to monsoon patterns could threaten food security for enormous populations, potentially triggering widespread humanitarian crises extending far beyond the immediate agricultural impacts alone. Beyond direct agricultural consequences, severe drought conditions carry cascading effects across entire societies. Water scarcity can intensify existing regional tensions, disrupt access to reliable drinking water, and force large-scale population displacement as communities search for more viable living conditions elsewhere. Climate researchers studying this potential scenario emphasize that Africa represents one of the clearest examples of how consequences from a weakening Atlantic circulation would not distribute evenly around the planet. While wealthy nations along the Atlantic coastline face serious challenges from rising seas and shifting storm patterns, some of the most severe and immediately life-threatening consequences could fall upon regions with comparatively limited resources available for adaptation. This stark disparity highlights an uncomfortable reality embedded within the broader Atlantic circulation story. The system driving these interconnected climate changes operates without any regard for national borders or economic circumstances. Yet the resulting consequences appear likely to fall most heavily upon populations least equipped to absorb and adapt to this kind of dramatic, potentially rapid environmental transformation. Deep within the Amazon rainforest, an intricate rainfall system has sustained one of the planet's most biologically diverse ecosystems for thousands of years. New research suggests this delicate balance could face significant disruption if the Atlantic circulation continues weakening, potentially altering rainfall patterns across South America in ways that could reshape this critical ecosystem. The Amazon rainforest depends on remarkably consistent seasonal rainfall patterns, cycling between distinct wet and dry seasons throughout the year. This predictable rhythm has shaped the evolution of countless plant and animal species, many specifically adapted to these particular seasonal timing patterns, developed over an extraordinarily long evolutionary history. Atlantic Ocean temperatures play a significant role in determining exactly how these seasonal rain patterns develop each year across South America. Changes to ocean temperature distribution, driven by a weakening circulation system, could potentially shift the timing, intensity, or geographic distribution of the rainfall the Amazon rainforest has relied upon for millennia. Some climate researchers have raised concerns about a particularly troubling possibility: that significant circulation disruption could potentially cause traditional wet and dry seasons across parts of South America to shift or even partially reverse from their historical patterns. While this remains one of the more uncertain projections within current research, even smaller shifts in seasonal timing could carry significant ecological consequences. The Amazon rainforest already faces mounting pressure from deforestation and rising regional temperatures. Adding significant rainfall pattern disruption into this already stressed system raises serious concerns among ecologists studying the rainforest's long-term resilience. Many rainforest ecosystems depend on relatively narrow windows of environmental stability, and substantial disruption to established rainfall timing could push already vulnerable regions past critical ecological thresholds. Beyond the rainforest itself, shifting precipitation patterns could carry significant consequences for South American agriculture more broadly. Countries across the region depend heavily on predictable rainy seasons for major crop production, and substantial disruption to these established patterns could create serious challenges for regional food security and agricultural economies. Scientists studying this potential connection emphasize that predicting exact regional outcomes remains genuinely difficult, given the complex web of atmospheric and oceanic factors influencing South American rainfall patterns. However, the broader pattern connecting Atlantic circulation health to global precipitation distribution continues appearing consistently across multiple, independent lines of research. This represents yet another example of how consequences from a weakening ocean current thousands of miles offshore can potentially ripple outward across the entire planet, reaching deep into one of Earth's most ecologically significant regions. The rhythm of rain across the Amazon, developed and refined across countless generations of evolutionary adaptation, may ultimately depend more heavily on the health of a distant ocean current than most people would ever expect. Far from the Amazon rainforest at the opposite ends of the planet, the Arctic and Antarctic ice sheets represent another critical piece of the Atlantic circulation puzzle. Research suggests a significant circulation collapse could trigger substantial changes to sea ice patterns at both poles, connecting this ocean system to some of the most remote, extreme environments on Earth. The relationship between Atlantic circulation and polar sea ice involves complex atmospheric and oceanic connections developed over the planet's long climate history. As the circulation weakens and northward heat transport diminishes, temperature patterns across the northern hemisphere shift in ways that can significantly influence how Arctic sea ice forms and persists throughout the year. Climate modelling examining significant circulation collapse scenarios suggests Arctic sea ice extent could actually expand under certain conditions, with ice coverage potentially reaching much further south than currently typical during winter months. This might initially seem to contradict the broader pattern of global warming, but it reflects the same regional cooling effect applied specifically to Arctic ice formation patterns. Interestingly, research suggests Antarctic sea ice, located at the opposite end of the planet, could experience a different pattern following significant Atlantic circulation changes. Rather than expanding alongside Arctic ice, some models project gradual Antarctic sea ice retreat under these same collapse scenarios, illustrating how a single ocean system's disruption can produce notably different consequences across different regions of the planet. This asymmetric polar response stems from complex atmospheric circulation patterns connecting both hemispheres. Changes to Atlantic Ocean heat distribution can shift broader global wind patterns and temperature gradients in ways that ultimately produce opposite effects at opposite poles, even though both regions remain connected through the same underlying disrupted ocean system. Beyond their immediate regional impacts, changes to polar sea ice carry significant consequences for the broader global climate system as well. Sea ice plays a critical role in reflecting sunlight back into space, helping regulate global temperatures. Significant changes to ice coverage at either pole could potentially influence global temperature patterns beyond the immediate polar regions themselves, adding yet another layer of complexity to an already intricate climate puzzle. Scientists continue studying these polar connections closely, recognizing that changes occurring at the most remote edges of the planet often serve as valuable indicators for understanding broader climate system health. The relationship between a weakening Atlantic circulation and shifting polar ice patterns represents one of the clearest examples of how deeply interconnected Earth's climate systems truly are, linking distant tropical ocean currents directly to the frozen landscapes at opposite ends of the globe. Throughout this exploration of the Atlantic circulation, one critical question looms increasingly large. Could this single system's collapse potentially trigger additional, cascading disruptions across other critical components of Earth's broader climate system? Climate scientists use the term tipping points to describe several major Earth systems believed capable of undergoing dramatic, potentially irreversible transitions once specific environmental thresholds get crossed. Beyond the Atlantic circulation explored throughout this script, researchers have identified several other systems potentially vulnerable to similar dramatic shifts, including large ice sheets across Greenland and Antarctica, and significant portions of tropical rainforests including the Amazon. What makes this concept particularly concerning is the potential for interconnection between these different tipping points. Rather than existing as entirely separate, isolated risks, growing research suggests these major climate systems may influence one another in ways that could potentially trigger cascading effects, where crossing one critical threshold increases the likelihood of triggering additional thresholds elsewhere. Consider the direct connections already explored throughout this script. Melting Greenland ice contributes directly to Atlantic circulation weakening. A weakened Atlantic circulation potentially disrupts Amazon rainfall patterns. Disrupted Amazon rainfall could further stress an already vulnerable rainforest ecosystem, potentially pushing it closer toward its own independent tipping point regarding large-scale forest dieback. This interconnected web illustrates why many climate scientists express particular concern about the Atlantic circulation specifically. Its influence extends far beyond ocean temperatures and regional weather patterns alone. It functions as a genuine connector within Earth's broader climate system, linking together multiple other critical components that might otherwise remain more geographically isolated from one another. Researchers studying this cascading risk emphasize enormous remaining uncertainty around exactly how these interconnected systems might interact under real-world conditions. Computer models attempting to simulate multiple interacting tipping points simultaneously remain far less developed than models focused on individual systems in isolation, given the extraordinary complexity involved in accurately representing these interactions. However, the theoretical possibility of cascading tipping points represents one of the most serious concerns motivating continued, intensive research into the Atlantic circulation specifically. If this system does serve as a critical connector influencing multiple other major climate components, then understanding and potentially preventing its collapse could carry consequences extending far beyond the direct impacts alone. This interconnected risk transforms the Atlantic circulation from simply one concerning climate story among many into something potentially far more significant, a critical hinge point within Earth's broader climate architecture, where disruption in one location could potentially reverberate outward, increasing risk across multiple other vulnerable systems scattered throughout the planet. After exploring dramatic scenarios involving frozen European winters, flooded American cities, and disrupted rainfall across entire continents, it becomes essential to step back and clearly separate confirmed scientific findings from legitimate, ongoing uncertainty still surrounding this complex ocean system. Several core facts enjoy strong, well-established scientific consensus at this point. The Atlantic circulation has genuinely weakened over the past several decades, confirmed through 2 decades of consistent direct observational data collected across multiple independent monitoring locations. Human-caused climate change, primarily through accelerated Greenland ice melt, disrupting ocean salinity, represents the scientifically established primary driver behind this weakening trend. Beyond these established facts, significant legitimate uncertainty remains regarding several critical questions. Exactly how much additional weakening will occur throughout the remainder of this century remains actively debated among researchers, with estimates ranging from moderate decline to potentially severe collapse scenarios. The specific timing of any potential dramatic transition remains similarly uncertain, with credible research supporting timelines ranging from just a few years to multiple centuries into the future. This range of scientific uncertainty does not reflect poor quality research or unreliable science. It reflects the genuine, extraordinary complexity involved in studying one of the most intricate physical systems on the entire planet, using direct monitoring technology that has only existed for a relatively brief period within the system's much longer natural history. Understanding this distinction between established fact and ongoing uncertainty matters enormously for how people interpret both current research and future news coverage on this topic. When new studies emerge describing dramatic potential consequences, these findings typically represent legitimate, carefully researched possibilities rather than guaranteed future outcomes. Responsible science communication requires holding both realities simultaneously, taking genuine risks seriously, while avoiding the presentation of uncertain projections as definitive predictions. This balanced approach matters particularly given how frequently dramatic climate stories can become exaggerated or oversimplified as they spread through public conversation. The genuine scientific findings explored throughout this script already carry enough weight and significance without requiring additional exaggeration. A well-documented 20-year weakening trend, confirmed across multiple independent monitoring stations, represents serious, legitimate cause for continued scientific attention and public awareness, entirely on its own merits. Scientists studying the Atlantic circulation continue advocating for exactly this kind of careful, honest approach. Acknowledging genuine uncertainty while taking documented risks seriously represents the most scientifically responsible path forward, avoiding both the dangers of dismissive complacency and the equally problematic dangers of unfounded sensationalized alarm. As research continues advancing, driven by improving monitoring technology and increasingly sophisticated modeling techniques, scientists remain committed to refining these projections further, gradually narrowing the considerable uncertainty that still surrounds one of the most consequential ongoing questions in modern Earth science. Every year, scientists add another layer of data to humanity's understanding of the Atlantic circulation. Monitoring arrays continue tracking temperature and salinity along the ocean floor. Satellites continue measuring sea level changes along vulnerable coastlines. Researchers continue refining computer models, incorporating lessons learned from the persistent pattern of underestimation explored earlier in this script. This ongoing monitoring effort represents humanity's best current tool for understanding exactly how close this critical system might be to a genuine tipping point. Early warning indicators, including the kind of physics-based signals explored earlier, continue receiving significant scientific attention as researchers search for reliable ways to detect approaching instability before a dramatic transition actually begins. Beyond monitoring and research alone, this unfolding story carries a critical human dimension worth emphasizing clearly. Nearly all researchers studying the Atlantic circulation agree on one fundamental point. Continued greenhouse gas emissions directly increase the risk of significant future weakening, while meaningful emission reductions could help preserve this critical system closer to its historical, stable configuration. This connection transforms the Atlantic circulation story from a purely scientific curiosity into something carrying direct relevance for choices being made today across governments, industries, and communities worldwide. The pace of future Greenland ice melt, the primary driver behind circulation weakening explored throughout this script, remains directly connected to the broader trajectory of global greenhouse gas emissions in the coming decades. None of this suggests any single choice or policy decision alone will definitively determine the Atlantic circulation's ultimate fate. The system's behavior depends on countless interacting variables, many extending beyond direct human influence entirely. But the scientific consensus remains clear that meaningful emission reductions genuinely can reduce the risk of the most severe, dramatic collapse scenarios explored throughout this script. Standing at this particular moment in 2026, with 2 decades of confirmed observational data now available, humanity possesses more direct evidence about this critical ocean system than at any previous point in history. This represents both a genuine opportunity and a serious responsibility. The opportunity involves using this hard-won scientific understanding to inform smarter, more effective climate policy decisions moving forward. The responsibility involves taking these documented findings seriously, rather than dismissing them simply because significant uncertainty still remains around exact timing. The Atlantic circulation has operated as Earth's hidden climate engine for thousands of years, quietly shaping weather patterns, coastlines, and entire civilizations across multiple continents. Today, for the first time in recorded human history, scientists possess the tools and data necessary to actually watch this engine in something approaching real time, tracking its health and stability with genuine scientific precision. What happens next remains genuinely uncertain, shaped by both natural climate variability and deliberate human choices still being made today. But one truth stands firmly established after decades of careful research. The choices humanity makes in the coming years will directly influence whether this ancient, powerful ocean current continues its historical role or transitions into something the modern world has never actually experienced before.